All right. Hi, everyone, mostly online. I would like to invite you to the seminar by Dr. Meng Li from Zurich Instruments. He's a Senior Business Development Manager at Zurich Instruments. He's received his PhD from ETH in Zurich in electrical engineering, mostly focusing, I think, on impedance spectroscopy. Today, he's going to talk with us about lock-in amplifier measurements and how that can be used to your measurement setup. So, thank you.
Yeah. Thanks out to Michael for the introduction and also giving me this opportunity to present our instrument and also this nice topic about lock-in detection at UTS. It's also my first time visiting Australia. I feel quite honored as well. So with that being said, let me actually quickly start on the presentation today. So to begin with, let me first introduce you briefly about our company. So in case you haven't heard about it before, actually, we were an ETH spin-off founded in 2008. Until now, we have about 170 colleagues and coming from really a multinational background, up to 25 or more nationalities. We are headquartered in Zurich in Switzerland, but also have offices in China, in US, in Germany, and also in Korea and Japan. And we are part of the Roden Schwarz family since 2021. So here, actually, you are seeing some of my colleagues already. Okay, moving forward, the instrument actually we offer from our company are usually categorized into 3 different pillars. So what Michael just mentioned to me, actually, to the audience here is the impedance analyzer, which I partially used during my previous PhD research. In addition to that, we also offer lock amplifiers, which is the focus of this talk, and also quantum computing control systems, what we call in short QCCS. If any of the audience are interested in this, be sure to reach out to me. We are also happy to discuss with you in the future. Okay, so let's see what's the next slide. So this slide here actually shows our current product offering for the lock amplifiers. So in terms of frequency range, as you can see from this horizontal axis here, it spans really a wide range from DC or 0 Hertz up to 8.5 gigahertz in the max frequency. In the low frequency, we have something called middle frequency lock amplifier or MFLI, which actually gives this more noise, better noise performance. And to middle frequency or high frequency towards ultra high and also gigahertz or super high frequency range. There, of course, the movement could be different, but the frequency are tuned to match your experiment needs. Keep moving forwards. So what kind of application do we can solve or can we help in your actual measurements? So as you can see, we also list a few different classes. So the most common way the instruments are used are in typical solid state physics, transport studies. But in quantum technologies, photonics, these are also often used. And more related to Michael, our devices essay research could be something related to the AFM or SPM, or towards sensors, more specifically speaking, maps. And here, actually, in below, you are actually seeing something which is a particle which is somehow attached to a carbon nanotube. This is often used in mass sensing, or you can also call it as a frequency-dependent mass sensing as well. Often there, the use of lock-in amplifier is quite demanded. Next to it, you are also seeing a cryostat or cryogenic electronics, where these kind of qubit chips can be also attached to our instrument, can be lock-ins or our QCCS, also quite useful here. So moving forwards towards the outline of this talk, I have already explained to you briefly about our company, and now I'm actually going to introduce to you about the lock-in detection principle. And from there, I will also briefly guide you through how to set up a proper lock-in measurement. And after that, if time allowed, I will also go through a few other techniques, multi-frequency or tandem demodulation. These are often used in both SPM applications and also some photonics applications. So let's actually start from here about lock-in detection. Why should we use it? Let's think about this scenario. If I send a laser light into a photodetector directly, what kind of response should I set? It's very likely that you will see something like this way. So the intensity, once before we actually pass it to the detector, is a constant, very high value. And if we insert a sample in between this kind of scheme, because of some attenuation, or you can also call it transmission, the intensity will decay. So over time, you will see a sharp drop. So this is the raw intensity we will detect if we put this detector right into a typical oscilloscope. But what happens if I'm actually measuring under or in, let's say, room light, right? If the room light actually is even stronger than my detected light signal, then I might end into trouble. This is actually not a good use of the measurement scheme, or we can also say the signal to noise ratio actually is smaller than 1, not so good. So how should we solve this problem? Of course, we know in almost all the optics labs, first thing actually is to make it into a dark room, switch off the room lights. But in addition to that, there's also something which we can do, really in case we can't switch off the room light or other perturbations. The idea is very simple. So we put the chopper in front of the sample. Yes, so you can see, because of the chopper, it's like a fan wheel always rotating. The intensity, of course, is modulated, becomes also this kind of sinusoidal wave. It might drop, but if I plot the amplitude of this intensity over time, not the intensity anymore, only the amplitude, we actually see the amplitude really follows the same trend. It's just really a very clear, sharp decay over time. And because only the laser source is modulated, the room light, the environmental noise, is not modulated. Therefore, its amplitude is not part of the measurement. And this is how we actually do this measurement, by removing the possible noise sources. And that is really the motivation why we should do a typical lock-in measurement here. So let's keep moving forward. Since I just briefly mentioned about signal-to-noise ratio, let's also discuss what it is about. So let me actually also make a bit clarification. Some people actually, they really define the SNR differently. So for example, there are people who call the relative change or the difference between the floor from the very left side to maybe the largest value there as their signal. This is possible and sometimes also allowed. But in our case, let's for the moment only call the absolute value of this measured amplitude as my signal. So the signal to noise ratio in this case will be defined by, let's say, the absolute value over the measured noise, the standard deviation. So if I put it into a log scale and multiply by 20, I will just get the decibel units value of this SNR. And typically, we will say a signal to noise ratio of greater than 1 is the bottom line where I can use these lock-in detections. So since I mentioned noise, you probably also are curious what typical noise which you may encounter in our measurement scheme. This includes minimum 3. So the first and obvious one is this 1 over F noise, or you can call it a pink noise. Some people like to call it this way. So in this chart as shown here, 1 over F noise is located on the left side, low frequency ends. In addition, we also have a background noise, which is saturating at high frequency ends. Some people call it as a white noise. And also we typically have noise spikes everywhere. This could be part of the source or pickup. Pickup can be often at 50 Hertz or 60 Hertz from the power supplies, or maybe radiations from nearby equipment in your lab. So this is possible. And of course, when we are doing measurement, our idea is really to use the lock-in amplifier to find the frequency, which is ideally free out of noise, and then use our built-in filters, low-pass filter or not filter, depending how you look at it, to remove these noise perturbances, therefore maximizing our signal-to-noise ratio, or SNR. So now actually we need to delve slightly into a bit deeper towards the physics or mathematics behind it. So the working principle of lock-ins actually looks in this way. Let's assume actually the above line in this light blue is my signal mixed with some whatever noise. And I also try to mix it with a pure, really ideal sinusoidal wave using the mixer inside. If I mix the signal in this way, what we can expect. So just a bit high school math. If you multiply 2 sine waves at 2 different frequencies, you can actually rewrite this equation into the summation or difference between 2 cosine waves. So as you can see here, there are 2 components. One is omega-1 minus omega-2, and there is omega-1 plus omega-2. So these 2, let's just in short call it the omega minus component, actually can be reduced to 1 if both frequencies match, right? So cosine 0 is really 1, And also that makes the result time independent. Time independent also means DC, which allows us really an easy measurement. And the other one, which is the omega plus components, in principle, you can remove it with either long time origin over infinity, or if you insert a low pass filter, as long as that filter bandwidth is smaller than this omega 1 plus omega 2, you can also remove it completely. And by doing that, I could just get this half R amplitude value from this measurement. And of course, a bit more physics here, or let's say I have some slides or figures later. If you put this into, let's say, change it from the polar units into Cartesian units, once you get the amplitude and the phase seed value, you could certainly convert it back into Cartesians X and Y. But of course, I mentioned about the R. How about theta? So actually the trend or the mechanism actually is very similar, since in the previous slides, actually we tried to multiply two sine waves. Now let's take a look at this equation again. I will change it slightly from two sine waves into sine multiplied by cosine. And in doing so, actually, you will end up with two, let's say, the difference between two sine wave components. And for this reason, because it's the sine value, as you can see here, if we go the same approach, set the two frequency as the same, you actually will end up a slightly different result, which is exactly the result from the previous one, but shifted by 90 degrees. Therefore, you can get, let's say, the shifted R by 90 degrees, or let's say the Y value. In doing so, actually, you will get both the X, Y, or R and theta, all four of them, from a single lock-in measurement at the same time. So that actually already defines us, or gives us the basic working principle of the lock-in amplifier measurement. What's next? So there is actually one very critical measurement as parameter in the lock-in setup, which is the filter bandwidth. And of course, you may also say the order of filter is also important, but maybe less important here. So as you can see here, I try to put the filter bandwidth or filter response over frequency in this kind of a log scale or body plot, you may call it this way. So a lower frequency or lower filter frequency means, let's say, a cutoff also at low frequency, which is on the very left side of these trees. If actually I plot the same response, also this FCO equals 0.1 on the time domain, actually the trend goes very oppositely, which actually means the faster measurement, or let's call it faster measurement in the time domain, is possible with a wide filter bandwidth, but in the frequency domain, because it's 1 over t is the inverse of it, it actually becomes very narrowly filtered. So I should say widely filtered, or nothing is filtered or suppressed. Counterintuitively, if I put it in the other way around, so if I insert a very narrow filter, then in the time domain, the rise time will be very long. So in that sense, actually, let me try to recap here. So how we choose the filter bandwidth in the setup really depends on what you want to do. It should be large enough possible to capture fast changes, so we don't have to wait for a very long time. And also should be as narrow as possible to possibly maximize the signal ratio by reducing the noise. So this again will take some thinking. And if you have any kind of thoughts or suggestions here, also please feel free to reach us out. Also happy to discuss with you. So I put the filter constants here, as you can see. The order of filter is partially on top of these 2 to the powers there. So it's actually partially of the equation. Also gives us the different time constant here as well. But because the 2 pi f3 dB is really there in the denominator, this is even more critical. So that's why I said the bandwidth actually is more important. So how this actually really affects our typical measurement. For example, this is actually a low frequency wave with high frequency modulation, or vice versa. You can also do this way. So you actually will see 2 different pulses, maybe a smaller one and a bigger one at a different time scale. And if you really open or zoom in these bigger pulses, you will see also multiple sine waves inside. It's a envelope. So if someone wants to measure or demodulate this result, ideally you want to get something like this. So the amplitude will look in this kind of very clear shape, and also the amplitude of both envelopes should be really close, let's say separated very clearly, one from another. However, different bandwidths really gives us different results. So what you see here is if I use filter bandwidth at 50 kilohertz, you will get the same result, but it just looks super noisy. I'm sure you can still read it, but maybe that's preferable. Let's say on the other hand, if I go to the opposite trend of 2 kilohertz in bandwidth, I still could see something, but as you can see, the signal is already quite distorted. And maybe at a certain point, I start to lose some information. That's not good either. And therefore, just to recap what I mentioned in the previous slides, balancing the choice of fast measurement speed and also signal-to-noise suppression is actually important. For this reason, actually, the bias performance here is given by the figure in the middle, which gives FCO 10 kilohertz. And as you can see here, it really gives both very sharp results and also reasonable low noise figures. So actually, that's just basically the working principle of lock-ins. Let's actually go to a more practical measurement in the lock-in and see how we should set this up. Starting from optics, I like optics because it actually involves more set of steps, which may need a bit more highlights. So I try to classify into 4 steps: reference frequency, signal conditioning at the input channel, low pass filter bandwidth, and save the results. So why I mentioned the reference frequency, as you can see here, typical laser measurement, just now I tried to also show you earlier, is I need to use a laser or let's say a chopper controller or maybe AOM or EOM to modulate my laser. Here, the chopper can be controlled or can control my lock-in in this way. So it can either take the internal reference from the lock-ins or output the reference to tell the lock-ins to synchronize it. So as you can see, these two are slightly different. So if you do an internal reference, what it means actually is the instrument can generate a sine wave by itself and output the TTL signal at the same frequency also by itself. If you go for external referencing, this is also possible. And your external reference does not have to be a sine wave. Often, actually, it can be a square wave or even very sharp pulses. You can also feed this to the lock amplifier as well, and internally map it with a phase lock loop, in short PLL, to the oscillator of the instrument. In this way, the instrument can still output the same frequency. So moving next, modulation frequency. In the previous figure, I already said some modulation is enough. At least for this typically chopper measurement, modulation frequency is not that important. But it is important, at least for us to avoid measuring at 50 Hertz. We know there's room line noise everywhere. That's quite obvious. But there's also something which we can do in these tools called scope, the built-in scope in our instrument, which allows you to see the result. For example, here you see almost everything's noise. Maybe it doesn't make sense. But if you put into frequency domain using the fast Fourier transformation, you will be able to see some signals. That could be something which we want to talk about, right? And remember, there's also something which is related to the measurement. Why I say the signal conditioning is important is the noise figures somehow depends on your actual setup as well, but also depends on the measurement instrumentation. And using the MLF example, I could use the green trace, which is maybe smaller input green at 1 microampere, rather than the 10 milliampere green in the red trace. It's clearly much smaller. And that also is one way to somehow improve our measurement results by internally, let's say, optimizing our measurement conditions. So moving to the next slides, I mentioned already about the signal conditioning, and this actually shows you the result. So as you can see here, this is actually the signal input port, which I just shared with you. We have different input settings, ranges, coupling, and also other setups. In addition to that, you may also want to know there's a gray bar, which is next to the voltage input band there, trying to give you a brief idea how much of the ADC is actually used. For example, if you see something like the left or right figure here, when the signal is overflow or underflow, neither would them sound really so great, right? So the ideal case really would be center your measurement signal into this gray bar. And that's another thing is also about DC and AC coupling. Again, in the same working example, this kind of optical measurement, often the photodiode is reverse biased. There could be some DC offset current easily, right? And using the AC coupling can also help us to center that zero. thereby allows us to measure in a smaller range, which also helps to improve the digitization, the DAC accuracy there. The next step, of course, is low-pass filter. I already mentioned. So filter bandwidth is important. Filter order is also important. This also gives you roughly results. The typical idea is if I reduce from 100 kilohertz to 1 kilohertz in the bandwidth, ideally the signal-to-noise ratio should increase by a square root of these 100 times. So basically, SNR should increase by 20 dB. Here, actually, you only see it increase by 16 dB because I'm already partially touching the measurement floor. So some of the white noise already goes into this measurement. Therefore, it doesn't increases that much, but still you could see some improvements quite clearly. And this is something, if this is helpful in your research, you can try to work in its operations. So let me also move to this last step, which is also important because naturally, when you finish your measurement, you want to write measurement result down. Of course, you could do it by a pencil and a paper, but our software also gives you the flexibility to do everything in the software. This can be a continuous trace or in a triggered events. In addition, you can also use either the graphical user interface which we offer, or some of the API tools which we offer as well, and then combine them together and achieving this kind of nice 2D colored plots or whatever plots you can have in your MATLAB or Python tools. So let's actually move forward to what's next we can do. So we already displaced how the setups looks like. And before I came here, actually, I asked one of my my colleagues to slides. Okay. Yes, to actually take a screenshot on how this looks like. So I mentioned actually, we actually start from signal conditioning. This is the results, which actually start from very rough, quite coarse sine waves, lots of noises. So first, actually, he tries to reduce the range by decoupling. And then he actually first reduced the range by this automatic signal scaling. And here, once she has done that, you can see the signal becomes much clearer than before. And once this is done, she can also proceed checking the reference of this instrument setup. Here, he used this reference trigger button to really look for the reference signal. And then in the input tab, try to change signal into this trigger input one as the actual reference source. As soon as she can do that, you can see the actual reference is on, the green LEDs next to it, and it's actually really fixed at 4 megahertz. Okay, so I mentioned about optics. Optics often is done with external reference, but there are certain cases where internal reference, or we call it internal source, is used. So this can be done in this kind of, let's say, low frequency transport measurement. For example, in this kind of measurement, which is often done in solid state physics, you can either connect your device in 2-terminal or 4-terminal configuration. A 4-terminal is also sometimes called by Kelvin type or Kelvin probe configurations, which gives a better removal of the contact resistances. And in addition, you can also use the upstream output ports of the Loki amplifiers to work as if additional gate voltage just to make a switch on and off your transistor type devices. And of course, this is typically done low frequency. So the result is often used by physicists to try to measure this transport in quantum dots, or they call it two-dimensional quantum gas 2DEX. So it's actually the same configuration, sweep the VSD, source free voltage, simultaneously with the gate voltage. The typical result actually is shared by also one of our customers from the UK, which I actually put here. So as you can see in this kind of 2D sweep, where you see some colored lines, those lines are really shows state in your quantum dots, showing that, okay, some conductance, some electrons or holes are flowing at these points. So of course, everything can be simulated or doing really in a real experiment. In this case, he used our Python API to do this kind of 2D sweeping. In addition to this, if you are familiar with transport or want to do transport studies, you could also consider this kind of RF reflectometry methods. So the difference from here to the earlier one is RF reflectometry is often done at higher frequencies. So this is actually given by our UHF local amplifiers. As you can see, this really involves low temperature measurements. You will need to use a few maybe steps to cool your setups or devices down to even milli-Kelvin temperature, many attenuations. But in the end, your device, which is actually shown on the bottom right of this figure, is a quantum dot. And in the circuit representation, we can just say this is just RC, right? And we know R and C, both of them are quantized. So the states can be set when you are at different bias or different conditions. So what that means is, if I've put a fixed inductance L there, when I sweep frequency, I will really see different resonance peaks or anti-resonance peaks because of these different capacitances, different quantum dot states, right? So here actually shows the sweep result. So as you can see, there are multiple spikes or multiple troughs. All of these actually gives an individual, let's say, different quantum states of your device. So let's actually move forwards. I already mentioned about transport and what's on top of transport, impedance. What is impedance? Well, complex resistance values, right? This is, of course, also one of the highlights of our local amplifiers because, I mean, as we all know, Ohm's law is very easy. It's even high school physics, but how it's measured often is actually not so well known. So in this case, let's just say I measure both the complex voltage and complex current. I used Ohm's law to divide the gap ratio. Then naturally, the ratio gives me, in the amplitude, the impedance value, and also the phase difference just becomes the phase angle in the impedance results. So why that actually makes the measurement special? Moving forward, so what do these people or many researchers need impedance for? Many of them, actually, if you are a device physicist or material scientist, you actually want to get some of these, maybe very likely the resistance or capacitance from the measured impedance value, right? So what it means actually is you need to infer these R and C values from the measured impedance using circuit models. And once you have done that, you can try to relate this R or C to your materials property. For example, the dissipation factor or dielectric constants in your materials, or defect states, trap levels, energy levels of your semiconductors. But what actually is often missing, remember, actually, I put this here for a good reason. If it's really only V over I, Ohm's law, maybe it's something that everyone can do. You don't have to buy a dedicated instrument for this purpose. So I put accuracy is key here because what we actually offer in our instruments is this nice resistance chart. So often this is actually overlooked. For example, if you want to measure, let's say, 100 picofarad, you can read across these 100 picofarad dotted lines. So you can see actually the measurement result really differs at different frequencies. At lower frequency, you maybe end up at very, of course, low frequency to capacitance is high impedance values. We're looking at the top left part of this chart. So you see we are somewhere at maybe 10% accuracy or 10% error zone. Whereas if you keep increasing frequency, maybe at kilohertz range or megahertz range, the impedance drops to kilo ohm level or 100 ohms level. There we are in this big white zone in the middle, which is given by the 0.05% accuracy. So this is something which we can really guarantee with the instrument and allows you to really trust on this measured impedance value. And only after this step can you proceed with the equivalent circuit modeling and get the R. Because without this, the R measurement or R derivation doesn't really make sense. And if the R derivation doesn't make sense, the next step of materials properties also is coming from nowhere. That would affect your final results in your publications. So I hope this actually is also something interesting to you. And if any of the audience are interested in discussing about this, also please feel free to reach us out. So moving forward, we could also share something about this resonance factorization. Resonator, as we know, is similar to the RF reflectometry I put in the earlier chart. It's something like the sweep frequency. I can expect different values in the peak values and amplitude and also the phase. We actually want to extract the resonance frequency and also the quality factors. But of course, there's also other ways to get it, for example, written down or PDH. So in this figure, as you can see here, we can use our built-in models to get this nice fit in these curved dots and enable us to calculate both the resonance peak and the quality factor. Quality factor is nothing more than the peak over the full width half maximum. I again asked my colleagues to give me some help to record it. So here actually you see a suite. So first, assuming actually we don't really know how the frequency of resonance locates, we just type in some value, 1.84 megahertz, not really. Already smooths the result quite significantly, and you get both phase and the amplitude in a single sweep at the same time. And then we can open the mask tab, just drag these cursors around the measurement resonances, and then get this resonance peak just by clicking this eyeball button. Once it's done, you see all the results come straight away. So both the center frequency for the resonance and the quality factor Q are given. So I already mentioned about this lock-in measurement. These are really the basics. Most lock-ins really would need them. So what's next? In the advanced applications, I want to share maybe one or two more things. So first, actually, is multi-frequency modulation or multi-frequency measurements. So if anyone of the audience actually is familiar with this figure, you may see actually some people call it as SNO. It's a scanning near field optical microscopy. So actually, you are using both mechanical and optical modulation to your ITM tip at the same time. There is often that these two are at different frequencies, right? So you end up at many spikes of these results, and maybe you want to measure them at the same time rather than one at a time. So our instrument actually has this capability to allow this multi-frequency measurement at the same time. All of them actually can come at a single click. So this again is a measurement here. So as you can see, assuming this is my result, maybe it does not make sense to you. This is also not the single sine wave, many sine waves mixed up together. And as you can see here, my colleague she's actually trying to do a more detailed frequency analysis, first by using proper triggers. So first he can use this maybe to link to the main carrier frequency of his optical modulators here at maybe 13 kilohertz or so. And then moving forward, maybe she actually wants to study the harmonics of this second order, third order, fourth order, etc. So as you can see, she's actually typing in 1, 2, 3, 4. So these kind of multiples of this base frequency, 13 kilohertz. And of course, if you want any arbitrary frequency, it could be modulation, at the 40K or so. He can also actually just type in this value by itself. And then in the plotter tab, it's actually possible to open all these demodulators all at once. So here, only the first demodulator at 13 kilohertz is shown. But I think in the next step, she's actually trying to add all the other demodulators just by click on this data transfer enable button. So as you can see, this demod 2, 3, 4, 5, 6, 7, all of them can be displayed on this tab. Of course, this is a mock-up measurement. These are not real data, but at least tells you that the instrument has this kind of capability. So on top of that, this is even more advanced way of using the instrument. It's called double demodulation. Again, it's often used by MEMS researchers. Maybe Michael is working on this way, and also some advanced AFM or optics researchers. So in this case, what people often do is try to mix a low frequency wave, maybe small omega, with the high frequency wave, capital omega. Usually, if you are familiar with the frequency mixing, you know actually the result of the mixing of these results are at least 4 traces in the frequency domain. So small omega, capital omega, and also the sum and the difference of the two. Getting all of these actually at the same time could be somehow difficult and challenging in the past. So in the past, how people do it is actually called tandem demodulation, which means one at a time. But in our instrument, it is actually possible to get all of them at the same time. In this kind of double demodulation, it's very often to mix 2 sine waves together, or maybe not more than sine, could be also other waveforms. But the result would be really complicated. So minimum 4. So these two sine waves intrinsically themselves, but also the difference and the sum of these, so 4. The traditional way to measure this is tandem demodulation, which actually means you will demodulate first time, maybe get one of these 2 omegas, and then follow with the second demodulation. In our instrument, actually, the highlights or unique selling points would be trying to really get all of them at once using these FM demodulation options. So here actually shows you the working flows of tandem demodulation. So as I mentioned, to get this result at capital omega, we just use the capital omega as my reference frequency externally, try to feed it into the instrument and doing a demodulation first level. And first level demodulation is like adding a notch filter or low pass filter, as I explained just now in the tutorial part. So this green envelope or this kind of green ellipsoid is just my integration error under or within my low pass filter bandwidth. By doing that, ideally, I should be able to get all the result signal strings within omega, plus or minus small omega part. And if I get this result, I will feed the demodulated result to a second lock amplifier in this way. And in my second lock amplifier, I will tell the instrument to read a small omega as my next reference frequency, and then do the demodulation again. Of course, in this case, in the second demodulation is lower frequency, I will again insert another low pass filter here given by this pink or purple envelope to do some integration. And again, hopefully to get the small omega components as well. So what's the possible limitation factor here? As you can see, first, you need 2 lock-ins. This is already a slightly more complicated setup. But even if you can tolerate that, there's still some physics which does not really, follows. So for example, here we actually are really assuming the ideal case. So there's no frequency dispersion of these results. So which means whatever frequency I can define using my low pass filter, all the signal can be integrated or included using my green envelope, and particularly this green one, and maybe manually on this purple one. But in case you do have some dispersion or what kind of statistics on these kind of results, maybe some of them will leak outside this integration loop. Therefore, in the second lock-ins, when you try to get the intensity, the result could be somehow erratic. And also, when you are doing this, then that's of course is difficult to plot in this figure. Is the phase coherence between the two actually is lost, because here actually I'm only trying to get the intensity, the amplitude. I didn't try to get a phase. Phase is not even possible in this way. So how to solve this problem? In our instrument, particularly MFLI or also other lock-ins, we actually can take 2 reference frequencies at the same time. So eventually, all these kind of data processing are done digitally on my lock-in amplifiers. So intrinsically, actually, I could just multiply the original waves with both these, omega minus capital omega minus small omega, and also capital omega plus omega at the same time, and also only doing peak integration around these 2 peaks. And of course, by doing that, I should be able to get both, this minus component and this plus component. And I know already beforehand, none of them is the difference, none of them is the sum. And therefore, just doing a simple math, I can get all these or both these 2 components out. So this, again, if I could recap, not only it simplifies the setup with only a single instrument, but also it allows us, let's say, more accurate measurement on the intensity of the result, and also keeps the phase coherence here. So actually, that's what I want to share with all the audience here today of my presentation. If you have any questions, I think we are still having 10 more minutes in these presentations. Please feel free to raise your hands, or if you want to type, if I can read it out, you can also type in here.
Unmute the microphone.
Go ahead. Any questions from the audience here? Feel free to ask. We still have 9 minutes ahead of time. Is there anything
I
which
might
is?
ask a question just
Go ahead, Michael.
for a general question.
Yes.
So can you explain maybe to the audience what is the most difficult frequency range to measure? Because you're continuously pushing your instruments to higher and higher frequencies. What is the limiting factors to go by going to higher frequencies, and what's the limitation maybe of measuring very low frequency signals?
Okay, so actually these are two questions. Let me actually just rephrase what Michael just asked me in case the remote audience didn't get it very well. So there are two questions here. First is why we are actually pushing the limit to go to high frequencies. And another actually is what's our typical limiting factor for measurement at low frequencies. So on the high frequency side, let me quickly go back to one of my slides just to show you our product roadmap and see how that could help. So let's actually many slides before. Yeah. Yes. So here actually what you can see our SHLI already goes to 8.5 gigahertz. And this is actually also our flagship. Nobody else in the world actually could make these high frequency log amplifiers. The main limitation, of course, is signal stability or signal measurement in a good accuracy at this high frequency range. So typically, many RF instruments, if they say they can measure at gigahertz frequency range, usually it's not from DC to gigahertz. It's from maybe 1 mic or 10 mic, sometimes even 100 mic to 10 giga. So low frequency results are all cut off by some built-in AC coupling. We don't want to do that because our instrument actually supports for more genetic researches, and there are really people who really need to use this full frequency range. If you insert a AC coupling filter, it basically blocks the measurement capability. So that's actually the high frequency limitation, is kind of full range requirements. On the low frequency requirements, actually this is also something quite special. So there we are typically talking to material scientists and also some physicists who want to study some very slow effect. Maybe let me give an example. Let's say electrochemistry. There people often need to measure at 1 millihertz. So, remember what I just mentioned about this measurement on maybe filter bandwidth requirement. If you want to measure at 1 millihertz, maybe the filter bandwidth need to be even smaller than millihertz. Let's just say 10 megahertz. And we know 10 megahertz in the time domain is 100,000 seconds. That's even longer than 1 day, right? So yeah, the instrument need to be really stable over this 1 day and really somehow gives continuous result, continuous measurement, and a good confidence on the accuracy as well. So that really makes things different. And this is also something which we have tested really seriously in our lab and also our factory, making sure everything is correct. Okay, that's actually my answers to Michael's question. I think we still have a few minutes of time. Feel free to ask, please. Are there any questions from the audience? Seems not, but I guess it's not a problem. Robin, so we will actually publish the link of this recording online. And on our site in Zurich Instruments, we will also make a small maybe social media post. And in case any of the audience here, or maybe some of your classmates or friends watch it, and if you have any kind of questions, feel free to reach out. And you can either write to me directly or just to our info line, our info box, write an email or make a phone call. Either myself or above my colleague would be happy to help you here. Yeah, great.
Thank you very much.
Thank you.
Thanks also for hosting me. I think we can close it from here. Yeah, also thanks all the remote audience for attending.